In this video, we'll be talking about some applications of matrices. Now, we've seen up to this point several ways to solve systems of equations, and really, in terms of matrices, we can actually write this as a matrix multiplication. Namely, we see that if you consider the system here, where we have the where all the A's, all the A1, A1, 2, all those, and the B's are all numbers, and just some scalars, and the X1, X2, and X3 are our variables. Think like X, Y, Z. Then we can always write that as actually a matrix equation of the form AX equals B. Namely, this would be our matrix representation, where this is our X, this is our matrix A, and this is our matrix B. And we've seen this before. Namely, we know that setting this up as an augmented matrix, we saw before when we did Gaussian and Gauss-Jordan elimination, etc. here. Then we could write this as the following, where we have B1, B2, B3, and then we would do row operations here to get an identity matrix actually here. And once we had that, we'd have our solutions then. So, for example, let's go ahead and write the system as a matrix equation. Let's go ahead and write the following system that I'm about to give you as a matrix equation, AX equal B. So here, the system is going to be this. And for this system, we know that we can write this as the matrix equation 1, -2, 1, 0, 1, 2, and 2, 3, -2 times x1, x2, x3 equals -4, 4, 2. And again, I want you guys to see that really what this is you're doing row by column. And if you do row by column, for instance, for the first one, we would have 1 times x1 plus -2 times x2 plus 1 times x3. And that would be the first entry of our resulting matrix here from the multiplication, which should equal -4. Well, what you'll notice here is that is precisely this first equation. If I was to do the second row by the column, I would get the second equation out by comparing it to 4. And then similarly with the third row and putting it into that column. Now, if we were to actually do Gaussian elimination on this, we would need to do Gaussian elimination on 1, -2, 1, 0, 1, 2, 2, 3, -2, -4, 4, 2, right? Because here, this is our B and this is our A. So this would be the matrix A, B. Okay? If you actually do a Gaussian elimination, I'm not going to go through all the steps because we've done this in several past videos, and hopefully by now you guys have done the homework as well, and or some of the suggested problems. And if you go through and do this, you'll have the following matrix. You'll get 1, and so the whole idea here is what we're really doing is we're reducing this down to the identity times some new form, which would be X. And we'll talk more in the next chapter, the next section, about what was really going on here, which is some sort of a matrix multiplication to get to solve out. But in the meantime, what we have here is 1, 0, 0, 0, 1, 0. So once we've done all of the Gaussian elimination, and then we'll end up with here -1, 2, 1. Which means this is our solution, x1, x2, x3. Namely, this is our matrix, or our column matrix X, that represents the solution. And now it's time for you to work an example. Go ahead and repeat the last example for the following given system. On the count of 3, I'll reveal the solution. 1, 2, 3. So going through, you see this is our matrix equation. Writing the matrix equation that way, I go through and I solve, doing row reduction, and I end up with with the identity matrix adjoined to X, which means this must be our solution, and I even went ahead and checked it up there. For a different sort of application of matrices, let's consider the following. Suppose you have two softball teams that submit the following equipment lists to their sponsors. All right. Now each bat costs $80, each ball costs $4, and each glove costs $90. Let's use matrices to try to figure out the total cost of equipment for each item. So here, we're going to write the equipment list as a matrix E, which would be 12, 45, 15 for the women's team, and 15, 38, 17 for the men's team. Here we have, what do we have? So we have E there. We also are going to go ahead and let C be the cost per item. If you let C be the cost per item, that list will be 80 for a bat, 4 for balls, and we need to correspond them here. So this is bats, balls, and gloves. This is per bat, per ball, per glove, which was 90. It's weird that bats cost less than gloves, but whatever. And then in order to get the total cost, it would be, well, we can't do E times C because that matrix multiplication doesn't make sense, but C times E does. Namely, we'd get C E, which is what? Well, if you go through and you actually do that multiplication, you would have 80 for 90 times 12, 15, 45, 38, 15, 17. If you do that multiplication out, you'll end up with 2 for 90. If you go through that, the first, if you do this row by the first column, and then if you do this row by the second column, you end up with 2882. And so what would this be? Well, here, because we totaled up the cost for the women's team, this is the total cost for women's team. And this will be the total cost for the men's team. Total cost for men's team. And so this gives you a useful way to deal with a lot of data at the same time is by using matrix multiplication. So now it's time for you to try an example. Go ahead and repeat the last example, same equipment list, but we're going to go ahead and have different costs this time. So on the count of 3, I'll reveal the solution. 1, 2, 3. Here we go ahead and have the same equipment list matrix. Here we have a different cost matrix. Going through, I went through and actually wrote out all of it and ended up with $2,310 as the total cost for the women's team and $2,719 for the total cost for the men's team. For more practice in working with these applications for matrices, be sure to see the textbook on pages 566 and 567 and work the suggested problems. In our next video, we're going to start looking at the multiplicative inverse for a matrix.